This video is for the Unit 11 Digital Interactive Notebook number 3. If you have chemistry on an odd day, this is for the May 20th lesson. If you have chemistry on an even day, it's for the May 25th lesson. We've got a 4-day week, the week of the 17th, and another 4-day week, the week of June 1st. So there's some odd shifting, but then they will line back up again by June 3rd, just in time for senior finals. So on the front cover, you put your name, and we go from there. So keyboard shortcuts, if you are having trouble seeing something, and I see this a lot walking around class, please do use the zoom in, zoom fit features. You can zoom in like this multiple times, and then scroll around to different things so they're nice and big and easy to see. And then you can also hit the zoom fit shortcut. And the zoom in keys are different on a Mac. And zoom fit, there we go. Please do use those. Also, using superscripts and subscripts are going to be important this lesson. So for example, if we write something like H2O for water, we want this 2 to be subscript. So I'm going to highlight the 2 and then use my subscript keyboard shortcut, which is holding down the control key and then hitting comma on a Windows computer like this. Then I can hit it again to make it regular text, or on a Mac I would hold down command and then hit comma to do that. Likewise, if we have something that has a positive charge, we highlight the positive and make it superscript by holding down control and tapping the period or the command key and the period if you're on a Mac. That also works for, say, if we had something that's negative, we could do that for negative sign, holding down control or command and tapping the period to make it superscript to denote charge. So we will be doing that on this notebook as well as the following notebook. Okay, so what is in this notebook? We're going to do some acid-base vocab review just on slide 4. We're going to redo the pH et al. Calculations. Et al. Is Latin for and the rest, so pH, POH, concentration of H+, concentration of OH- in solution. So we'll do that, and then we'll talk a little bit of review of where the H+ and the OH come from, and then we'll get into some predicting the products. So there are 7 words here. I will give you 4 of them, and you can figure out the rest. So aqueous chemicals that remove H+ cations and increase the concentration of OH-, those are bases. And there are aqueous solutions that are higher than 7 on the pH scale. There's 2 that fit in here. One is short for the concentration of monatomic hydrogen cations in solution, and that is the concentration of H+. And remember, I need to select this plus and make it superscript. And then the other one here, short for the concentration of polyatomic hydroxide anions in solution, is the concentration of OH-. And again, I select that minus sign, and I hold down control and tap period or command period on a Mac to make it superscript. The concentration of OH- ions is equal to 10 to the negative POH. That is our POH definition. And an acid or a base that will completely dissociate, 100% of the molecules dissociate, that is a strong acid or base. So we used POH, we used bases, we used strong, and we used the concentration of H+ and OH-. You can figure out where the other 3's go using the comparisons with the words that are already there. Pause the video now and finish that. Okay, slide 5 through slide 10 is us redoing the different calculations from the end of the last din where they were done somewhat poorly. So, Each one has a learn section, an example section, and a practice section. The learn section tells us which variable you know and which variable you're trying to find, and then which equation to use. Then the example section shows using that equation. So, on this slide, if you're trying to find, if we have pH and we want to find POH, then we'll use 14 minus pH equals POH. So in my calculator, I will type in, for example, 14 minus, and then instead of pH, I write down what my pH is. So 14 minus 10.82 equals 3.18. So my POH is 3.18. So for this practice one, hello Beruria, if the pH of a solution is 5.53, then what is the POH of the same solution? So POH, we know the pH. The pH is 5.53 because the question told us that. How? So now how do we find the POH? Well, our equation is 14 minus pH, because it says over here 14 minus pH equals POH. But our pH, we have a number for our pH, so we replace pH with that number, 5.53. We hit enter on the calculator, and we find what the POH is, like that. So pause the video now, put this in a calculator, and write down what the answer was. Okay. Slide number 6 uses a very similar equation. 14 minus POH equals pH. If we know the POH and we want to find the pH, we use this equation. So, for the calculator, we use 6.33 is our POH. So 14 minus 6.33 gets us 7.67. If you need a calculator, you can just click right there and get a calculator. Okay. Remember to type in this box right here what exactly you're typing in the calculator to get the answer. Fill out the POH from the question, do the calculations, and find the pH. Pause the video now and do that. Beruria. Beruria. Good kitty. Okay, so on slide 5, the equation to find POH, and slide 6, the equation to find pH. Those equations are very similar, as are the equations on slide 7 and slide 8. Slide 7 and slide 8 are to find the concentration of H plus cations in solution, or to find the concentration of OH minus anions in solution. So to find those concentrations, we have to know pH to find the concentration of H plus, or we have to know POH to find the concentration of OH minus. So our equation would be 10 to the negative exponent of pH equals the concentration of H plus. So we put in 10 to the negative whatever our pH value was equals that concentration. So let's zoom into the example here. So we want it to read 10 to the negative 6.88 because 6.88 is our pH. So we type 10 and then we use this key, x to the y, to get to our exponent, negative 6.88. We hit equals. It's going to give us a number of 1.3182567 E minus 7. The E minus 7 at the end is very important. Don't get rid of that E minus 7. So we're not going to use all of those digits there. We're going to round it to 2 decimal places, but we're going to keep E minus 7. So instead of 1.318, we're going to round this 1 up to a 2 because the number after it's higher than 5. So 1.318 becomes 1.32, and we keep the e minus 7. E on a calculator answer, not to be confused with the E key. Please do not use the E key. It will give you the wrong answers. E means times 10 to the. So E negative 7 means times 10 to the negative 7th power. So E negative 7 is times 10 to the negative 7th power. So 1.32 times 10 to the negative 7th power would be an answer. This negative 7 means that we're going to move the decimal point 7 times to the left. So what that would give us is 7 zeros, including the 0 before the decimal place. So times 10 to the negative 7 means we're going to have 7 zeros, including the 0 in front of the decimal place, before we get to our first number from here. So our answers could be really any of these three: 1.32 e to the negative 7, or 1.32 e minus 7, or 1.32 times 10 to the negative 7th power, or 0.000000132. All of those would be correct answers. So for this one down here, if the pH of a solution is 7.52, then what is the concentration of H plus cations? Our pH is 7.52. And what should we put in the calculator? Well, we should put in 10, and then we want to do the to the. If we want a calculator, we can click here and get a calculator. But in our slides, we want to make this superscript, so we'll hold down Control or Command and hit period, and then we can write in negative 7.52, because it is 10 to the negative pH. So we put that in our calculator. We're going to get an answer with a lot of decimal places. So we're going to get some number, point, some number, some number, something like that, E minus, and then another number. So a lot of decimal places here. Just whatever you put in your calculator, you'll get that out. And then when we round it to 2 decimal places, we're going to round it to something, point, something, something, and then we're going to keep the E to the minus something. So whatever numbers you would round, those go in there, and we're going to change that to, something, point, something, something, times 10 to the negative something power. And then we're going to write that out as a decimal, so 0.0, however many zeros there were right here, and then these 3 numbers at the end. And any one of these 3 we could write as our concentration of H plus ions. So pause the video now, put that in the calculator, do the rounding and rewriting steps, and then we'll go from there. Okay. Hi. If you're feeling stuck, do examine the example. Examining the example can help you figure out how to get yourself unstuck. So follow the directions, the steps written out here, and those same directions are done in the example for you. Okay. Then on slide number 8, it's the same type of equation, but with POH and the concentration of OH minus. So pause the video now and do that. Okay, for slides 9 and 10, we're going to be using the concentration of ions to find either the pH or the pOH. And we're going to use negative log base 10 of the concentration is going to equal our pH. So, for example, if our concentration of H plus ions is 4.82 E minus 5, we're going to type in negative and then the log key. Let me zoom in on that actually. We're going to type in negative and then log, and it'll give us this parentheses 4.82, and then it says E minus 5. Do not use the E key on the calculator. That will give you an exponent derived from the natural log, and we don't want to use that. That'll give you a weird negative number. So instead we want to do negative log 4.82 and then times 10 to the, we use this key to get the exponent, negative fifth power, and then we hit enter. It'll give us this long decimal 4.31695296176. We can round that to 2 decimal places. This 1 here, the number after it is bigger than 5, so we round it to 4.32, and that is our pH. So when you're calculating pH and pOH, the pH and pOH numbers should only ever be between 0 and 14. They should never be negative. If you're getting a negative number for your pH or pOH, then you have calculated it incorrectly. So for this one here on slide 9, our concentration of H plus is 7.05 E minus 8. And so what we're going to put in our calculator is we're going to put in negative log, and then in the calculator is just automatically log base 10 unless you make it something else. So we can just do negative log of the concentration, which is 7.05, and then I'm not going to use the E key. I'm going to say times 10, and then in superscript, I'm going to say negative 8, and then close parentheses. So after I put all that in the calculator, just like that, I should get a number with a long decimal. It's going to be a positive number. It's going to be a positive number between 0 and 14. If you didn't get a positive number between 0 and 14, you typed it in wrong. Make sure you're using times 10 to the negative, and whatever this is here, and not the E key on the calculator. So pause the video now and work on this slide. Okay, slide 10 works much in the same way. We're just using concentration of OH minus anions and the pOH. So use the same steps you used on slide 9 on slide 10. Pause the video now and work on that. slide number 11. Good work on those calculation slides. It's a lot of work to do those kind of calculations. It's putting your head in an equation space. You know, you're getting these numbers. Some of them are very, very small. Some of them have a lot of decimal points. A lot of them have exponents. It's a big mind warp. So we just talked about how we use pH and pOH to measure the concentrations of H plus and OH minus in solution. And remember, a solution is we've got some water, H2O, that has stuff dissolved in it. And the water itself dissolves in the water. H2O, 2 hydrogens and 1 oxygen, dissolves into H plus cations and OH minus anions that, if they come back together, becomes H2O. It's a reversible reaction. So these are some equations we looked at in the first and or second notebook of this Unit 11. So this is an acid because it has more H plus ions than it has OH minus ions. And an acid, if we have, H and then A, will dissolve and dissociate into an H plus, an additional H plus. That's how we get more H pluses than OH minuses, and then the negative part of the acid that fell off. A base over here, this has more OH minus ions than it has H plus ions, so it is a basic solution. And we have whatever the base was plus water. The base is going to remove an H plus. It pulls one of the H's off the water and sticks it onto the base, giving us an additional OH minus anion. So that is the basic overall function of acids and bases, but there are 6 more specific reactions that we're going to be looking at for the rest of this notebook. So, acids, this slide 12 is just kind of a menu of the things to come, a little bit of preview of what's in the rest of the notebook. So, on slide 13, acids dissociate to form a proton and a conjugate base. Slide 14, weak bases and water form a conjugate acid and a hydroxide anion. Slide 15, strong bases dissociate to form a conjugate acid and a hydroxide anion. Slide 16, strong acids and strong bases will form a salt and water. Slide 17, acids and active metals form a salt and hydrogen gas. And then on slide 18, acids and carbonates form a salt and water and carbon dioxide gas. So, on each of these slides, again, we're going to have a learn section, an example section, and a practice section for all 6 of those reaction types. And then we get into conjugate base pairs. So on slide 13, acids dissociate to form a proton and a conjugate base. So we've got HX as our acid. It's aqueous. Will dissolve after its reaction, will form H+, which is just a proton. Aqueous plus a conjugate base, whatever the rest of that acid was, aqueous. So, some examples of that. We can predict the products that form when these acids dissociate. If we have HBr, well, they always form a proton, so H+, which means this H fell off the Br, and now we have Br-, and they're both aqueous. If we have something like H2SO4, if just one of those hydrogens fall off, we have one hydrogen that fell off, and then we have HSO4- as aqueous, because that's what's left. One of these hydrogens goes away to become over here, so instead of H2SO4, it is now just HSO4, meaning there's one hydrogen left. So, when we predict the products that form when these acids dissociate, we know that when HF, or hydrogen fluoride, dissociates, one of the things it's going to form is H plus aqueous. And remember, we want to make that positive sign superscript, so we're going to pop it up like that. And we want to make the state symbol aqueous subscript, so we're going to pop it down like that. If you don't remember how to do those, please check the keyboard shortcuts for superscript and subscript text on slide number 2. And then, after the H plus falls off, what's going to be left from the acid? Well, the only thing left we're going to have is going to be an F for fluoride. And because this positive thing fell off, it has to be negative, and it's in solution, so it's going to be aqueous. And remember, aqueous needs to be subscript, and the charge needs to be superscript, like that. So I believe you can do the other two examples for HNO3 and HC2H3O2. For this HC2H, for the last one, this HC2H3O2, just the front hydrogen is going to fall off. These hydrogens in the middle here will not fall off. They will still be part of the conjugate base. All right. Pause the video now and work on slide 13. Brewery. Okay, on slide 14, weak bases and water form a conjugate acid and a hydroxide anion. So we start with a weak base. X just stands for whatever the base is. And then when we add water, H2O, which we have 2 hydrogens and 1 oxygen, it's liquid, so that is water. And then that becomes, after the arrow, XH plus, which is our conjugate acid, which means one of these hydrogens came off water and got stuck to our base, represented by X, plus OH minus, that is the hydroxide anion. So, predict the products that form when strong acids and strong bases react. Oh, that is the wrong directions. The right directions are up here. But anyway, if we have NH3 as our weak base plus HOH as our water, one of the hydrogens falls off the water and gets added to the NH3. So NH3 plus another hydrogen is NH4 with a positive charge, and that's aqueous. Plus water, if we take off one of the hydrogens, we get OH minus aqueous, that is the hydroxide cation. And we can see here at the bottom on slide 14, if our base here is HONH2 aqueous, and it has HOH water as a liquid, one of the hydrogens falls off the water and gets added, so NH2 becomes NH3 plus. That's how weak bases work. And then we've got the OH minus aqueous over here. So when we're predicting the products that form when these weak bases dissociate, we know that when we have H and OH, when we know that we have HOH and it dissociates, it's going to become, instead of HOH, one of the H's falls off and we're just left with OH, and we're going to make sure we know that that is negative and aqueous, remembering that aqueous should be subscript and the charge should be superscript. Over here we're going to have the conjugate acid, which is C2H5NH2, and remember to make all those numbers subscript. But because the H fell off this water, it used to be HOH, the H fell off and comes over here, so instead of NH2, it's going to be NH3. And because we added that extra proton, it's going to be positive, just like it was in the examples and the directions. So pause the video and do these next two practice problems on slide 14 on your own. Hi, Goofy. And get unstuck. You trying to eat the microphone? Don't don't eat the microphone, Goofy. Okay. On slide 15, strong bases dissociate to form a conjugate acid and hydroxide anion. So here we have a strong base, whatever the X was, and then OH will dissociate to form a conjugate acid, which is X plus, whatever the X was, and the hydroxide anion, OH minus. For example, predict the products that form when these strong bases dissociate. If we have LiOH, and that's aqueous, it will dissolve to form Li plus AQ plus OH minus AQ. This example down here is a little wrinkle in it. When we have MgOH2, because the OH is in parentheses, that means, a group of OHs, and the subscript 2 means there's two of that group of OHs, which means we're going to have two OH minus, because, they're not bonded together with that Mg anymore. They're just out loose in the world, so the subscript is going to become a coefficient. And because we had two of these OH minus things, to balance out two negatives, we need a positive 2 charge on the magnesium. One of our practice problems is like that. I'm sure you'll be able to figure out which one. So when we're predicting the products that form when these strong bases dissociate, we know that one of them is going to be OH minus, and that's going to be aqueous. And we have to make sure that it is subscript on the aqueous and superscript on the charge. And then if the OH minus fell off, all that's going to be left here is our K, and that is going to have a positive charge and is also going to be aqueous. And remember to do subscript and superscript for the charge and state. Okay, pause the video now and do NaOH on your own and SrOH2 on your own. Go ahead. Okay, on slide 16, we have strong acids and strong bases form a salt and water. So here's a strong acid. We know it's an acid because it starts with an H. Here's a strong base. We know it's a strong base because it ends with OH. And then the salt forms from whichever the non-HOH part of the acid and base was. And then water is the HOH part of what the acid and base was. So predict the products that form when these strong acids and strong bases react. We have HCl, aqueous, plus RbOH, aqueous. We're going to form water, HOH, so the H from the HCl and the OH from the RbOH will form together. And then what's left over, we have the Rb and the Cl will form together in a nice double replacement reaction. We also have that happening down here with the HNO3 and the KOH. The H at the beginning of NO3 and the OH at the end of KOH form together to make water, and the parts that are left, the K and O3, comes together to be aqueous. All right, so predict the products that form when these acids and strong bases react. Well, we're going to take the H from the HI, and it's going to go right there, and the OH from the LiOH, and it's going to go right there. And water is not aqueous. Water is a liquid. So we'll put a little L there to show that it is liquid. And make it subscript. Water being aqueous wouldn't make much sense because that's water dissolved in water. It doesn't make any sense, so we'll call it a liquid. That water dissolved in water thing is also why I say water isn't wet. Water makes things wet because water doesn't dissolve in water, but that's a whole other argument. And then if we take that H and OH off, what's left is we've got our Li and our I, which will be aqueous because it should be nice and dissolved in water. Hooray! Though if we wanted to be super sure, we'd use one of those solubility charts from Unit 6, but we're not going to do that just yet. All right, so you should be able to do these next two on your own. And while this last one, this H2SO4, is officially diprotic, we haven't learned about that yet, so just one of these H's is going to fall off and make HOH. The other H is still going to stay on H2SO4. So pause the video now and work on slide 16. All right, on slide 17, we have acids and active metals form a salt and hydrogen gas. So we have whatever the acid is and whatever the active metal is. Note that it's a solid, and then it's going to form a salt of the metal ion and the conjugate base ion, and then hydrogen gas of H2 gas. So predict the products that form when these acids and active metals react. If we have 2 HCl plus Mg, the two hydrogens here are going to form hydrogen gas, and then we're going to have Mg as our metal, and then this 2 also applies to the chlorines, so we're going to end up having 2 chlorines. So MgCl2 aqueous plus H2 gas. If we have H2SO4 aqueous plus Mg for magnesium, both of these hydrogens can fall off H2SO4. It's what's known as diprotic, which we'll get into later. So we can just take off the H2, put it over here, and the SO4 and the Mg will also form their own salt. So if we're predicting the products that form when these acids and active metals react, we know that because it's a metal and an acid, these two hydrogens are going to come off and they're going to make H2 gas. And we need to make the 2 and the gas both subscript. And then what parts are left? Well, we're going to have Zn is going to be our metal, and then Br, there were 2 Brs over here, so it's going to be Zn, Br, and then subscript 2, and it is aqueous. All right. For the next one, because it starts with H2 and both of these hydrogens can fall off, our answer is going to look a lot like the answer did down here for the MgSO4. All right, pause the video now. Finish slide 17 on your own. Okay, on slide 18, acids and carbonates form a salt and water and carbon dioxide gas. So we have an acid, something H, and then whatever the conjugate negative anion is. And then we've got a carbonate. Carbonates are, usually some metal and then a CO3 ion at the end. So whatever these two X's were will combine to form a salt, and then we'll get some water, and then we'll get some carbon dioxide. So if we have 2 HBr and CaCO3, or calcium carbonate, we're going to take off the calcium, and we're going to take off the 2 bromines from over here to make CaBr2 aqueous. We're going to make some water, HOH, so these 2 hydrogens plus one of these oxygens from CO3, and then we'll be down to CO2 as a gas. And we can do the same thing over here where we have 2H, C2H3O2 plus Li2CO3. We know we're going to get CO2. We know we're going to get HOH as water. And what's going to be left? Well, we'll have 2 of these lithiums, so Li, and then we're going to have 2 of these C2H3O2s, so 2 LiC2H3O2 aqueous. So, predict the products that form when these strong bases dissociate. We know that we're going to get a CO2 gas that comes off. We know we're going to get some liquid water that comes off because it is a carbonate reaction, and that's what happens there. So now we just need to figure out what the salt is. Well, iron is still going to be there, so we're going to have some form of iron, and then we're still going to have 2 chlorines left, so it'll be FeCl2 aqueous. All right. Pause the video now, look at the examples, and do the other 2 problems on slide 18. All right, slide 19 and 20 are about conjugate acid-base pairs. An acid is, a hydrogen on another cation, a hydrogen and an anion, that if it releases the hydrogen, you release the H+, you get a conjugate base, which is a anion over here. And it's a conjugate base because it is possible for it to absorb the H plus back and become the acid in a reversible reaction. Likewise, if we have the base that absorbs an H plus, then it becomes a conjugate acid, and it's called an acid because it can release that H plus in the backwards reaction. So the base and the conjugate base are both bases because they both absorb H plus ions. The acid and the conjugate acid are both acids because they both release H plus ions. The acid releases the H plus ion in the forward reaction. The conjugate acid releases the H plus ion in the backward reaction. The base absorbs the H plus in the forward reaction. The conjugate base absorbs H plus in the backward reaction. So how can we use that to identify the conjugate acid-base pairs? So we have an example here. We've got HC2H3O2, which is an acid because it begins with H. We've got H2O, which is our base. Water can be an acid or a base. If water is next to an acid, then that water will act as the base. If water is next to a base, then that water will act as an acid. So over here on this side, our conjugate base is the one that could absorb an H+. So C2H3O2, if we put a hydrogen on there, that means it absorbed that hydrogen and it becomes this acid. So that would make it the conjugate base. And likewise, this is the conjugate acid, H3O+, because if it loses that one of the hydrogens, then it becomes H2O. So it's able to donate that and able to become the conjugate acid. So figure out what these other 2 are based on if they will be releasing an H+, or if they'll be absorbing an H+. Pause the video now and work on slide 20. Then on slide 21, just to check in. How's it going? How are you feeling? Need anything? Let me know. All right. That's it for this video. Email with questions. Okay, thanks. Bye.